Okay, this is part 4 of Backyard Roller Coaster Physics, Math, Engineering, STEM course, part 4. So now we've done enough physics and math to know kind of what we want our out and back roller coaster to look like, the heights of different things and the turn radius. So we can now kind of enter the engineering side of that and how we're going to make this roller coaster. And the big decision here is whether you and your class want to make just a model roller coaster that nobody rides on, which is much cheaper and safer, or do you want to build one that you can ride on? It's going to be more expensive, and there's going to be a bunch of safety things that we have to talk about. But that's, part of engineering. You need to involve your parents and your school to see if they're willing to let you take this risk of a real rideable roller coaster. This is a very small roller coaster. It's not going to kill anybody if it does not very high and doesn't involve that much energy, but you could still get hurt. So very important to follow the safety. And if you have good engineering, that's a lot of the safety concerns. So I did a previous version with a model roller coaster, and we'll see a couple pictures of that. But this presentation is mostly about a rideable cart and track. This is the previous one. This is just a PEX, 3/4 inch PEX, I believe, and these little wooden ties, and just the students put it together in. And then I designed a wooden cart. These wheels were really cheap, but they did not work very well at all. I would redo this. I would find some decent wheels and maybe redesign this so that it went better than this one did. The front, this is a two-dimensional coaster, but the front you can see here pivots. The reason for that is if you have this pivot, then all 4 wheels will have the same load in them. If you just design a cart where all 4 wheels are fixed, 3 points define a plane. And you can't make the track or the cart perfect enough that you could have even loading on all 4 points. So what this bar in the front does that pivots in a roll degree of freedom, that makes it so the wheels are always evenly loaded, which is better for stress. It's better for the track. It's better for lower friction. This is the 3/4 inch PEX track. This is just plumbing pipe, modern plumbing pipe called PEX. And the students made this and then ran it. And you can do all the science with this. You can see how fast it's going and how high it gets to at the run out and everything. And you can even put instrumentation on it. You can, we'll talk about instrumentation and taking videos of it and deciding how good your analysis was. But you can't ride this. So a rideable roller coaster. First thing to talk about is wheels. I generally use the 70 millimeter longboard wheels as hard as you can find. They don't come really hard, but you want to get the hardest ones. And you always want a flat surface on all the wheels because it's going to interface with a round tube. And you don't want, you want anything but a flat surface. It won't ride right in the middle unless you have a perfect track and a perfect cart, and so you have to have some leeway there. You can have main wheels that are smaller than 70 inch. I think these are around 50 to 55 millimeter diameter, but you want the hardest ones you can find. I think there's a certain kind of roller skate wheel for indoor going really fast, and they go up to A101 hardness, but try to get something as hard as you can, and that'll be less friction. I did some of my carts, I made the side and upstop wheels out of 1/2 inch PVC electrical conduit couplers, an 8 millimeter bearing, which I think is 22 millimeters on the outside diameter, if you heat this up with a torch just a little bit, you can poke this bearing in the end there, and it'll stay there. Well, if it takes some practice to do that well. It just needs to be in there really flush with this bearing needs to be flush with the end of the coupler. That's a cheap wheel you can make, and you could scavenge these out of a thrift store. These wheels, but like I say, try to get the hardest ones you can find. Okay, this was a cart I designed a long time back, but I never did make it. I don't know why it couldn't be made though. But you can basically see these wheel brackets are made of 1/8 inch thick steel. I usually get a rectangular tube and then just cut them away. I don't have to bend that angle on the U-shaped bracket. Then you get all these pieces, design it. I do have this design I could give somebody. You can see there are steel sleeves welded into this assembly. These are long steel sleeves that almost all of the fasteners you use are going to be grade 8 5/16 fasteners, and you can see where you weld these things together, and there you have your main wheels, your side wheels, and the upstop wheels. The planned gap for the side wheels, so we know that the main wheels are going to ride on the track, but you can't make the track or the cart to tight enough tolerances to where this is really close in here. So I leave an 1/8 inch on either side, or 1/4 inch total gap between the side wheels and the track, an 1/8 inch on each side, and then I leave a 1/4 inch on all the upstop wheels so they never bind on the track when it's going over a hump or in a dip. And that seems to have worked pretty good. This is pretty straightforward to a person who welds, and these are tube steel, and I can give you this design or put it somewhere. This is a close-up of the corner, the assembly. You weld these steel sleeves in, put a throwaway fastener inside the sleeve when you weld it, and that'll take some of the heat away. Anyway, I recommend getting into welding. There's cheap welders at Harbor Freight, and you can learn to weld and buy a dimmable welding helmet and buy the protective clothing, and for a couple $100 you can look on YouTube and get in the ballpark of beginning welding. So this is a little more detail about the wheel brackets, made from 2.5 by 2.5 inch by 1/8 inch square steel tube, which you can get from a steel supplier, and then you use thin grinding wheels to cut them into the shape you want. You don't have to do any bending or forming in this design. These major frames I made from 1.5 by 1 inch by 0.63 steel tube. And then, anyway, just take a look at this. You can stop the video and take a look. And then I think this thickness of this tubing can be as small as 0.63 if you can weld that, but can be thicker, 0.80 or 0.125, 1/8 inch thick. This is, you can see this was for a smaller track actually. The track I'm proposing that students build is 18 inches gauge, the track gauge. That's from center to center. It would be 18 inches, not this smaller gauge, which is the one I built early on. So you can see that there's an 1/8 inch gap between the track and the side wheel on either side, so a 1/4 inch total, and then a 1/4 inch gap between the track tube and the upstop wheel. that's probably good enough so that it'll slide and won't bind up, unless you really make your track poorly, and then you'll need bigger gaps. This shows a 31-inch long, but I think the 30-inch length from wheel to wheel, that's pretty small. I for adults, I'd go more like 36 or a little more maybe. And so I thought some people might not want to learn to weld, and so I designed a 4-wheel, 2-dimensional cart that could be fastened together. Welding, you really start to appreciate welding when you see how many fasteners you have to use to replace welding and how much they cost and how much they weigh. So the welded cart is lighter and cheaper. But, you could make a fastened cart, and this is a design. The steel alone in here weighs 27 pounds, quite a bit more than the welded design. And then you have the weight of the 56 bolts and everything. The steel here, the tube steel, I'm estimating it cost around $100. And then I thought it'd be really interesting to, if somebody was going to make an aluminum stem cart that was fastened together. Now, you can weld aluminum. I think it takes more skill than steel, but that would be a really nice cart as an aluminum cart. And you could do that you copy the designs of, I've made like 50 of these different designs on these carts, and you could find one that you could make in aluminum pretty quick. It's basically a similar design to my steel tube cart, but it uses all 1/8-inch thick aluminum, because aluminum's quite a bit lighter, a third of the weight of steel, and so you can make it thicker and still come out. So I saved, I think, 12 pounds on this over the steel one. Oh, the aluminum parts would cost 12 pounds. That's all they would weigh. And but then you add the wheels and the fasteners in. The aluminum parts here, the square extrusions in aluminum, series 6000 something, are probably going to cost quite a bit, maybe $300, but it's going to be lighter. And this is a fastened design that I'd like to see somebody try. And here's some details of it. All the wheel axles on both the steel and the aluminum ones. I think you can put a fastener in a pattern like this that's closer to the edge, and maybe you don't have to support that tube through the fastener. But most of these, especially where you have a wheel axle, there's a steel or aluminum tube supporting the compressive load of the fastener itself, so you won't crush these open sections. And so there's a sleeve on either side of the wheel to keep the wheel in those. It's critical to keep the wheel from rubbing on the bracket. So there's some steel sleeves in there of the correct distance, so the wheel stays in between the two. And then there's a steel sleeve on this wheel, top and bottom, and a sleeve in here, and a sleeve that goes out there to a cantilevered upstop wheel. And then there's 1/4-inch fasteners in here near the edge, so you probably don't have to support them with a sleeve. But anything through like here, well, that only goes through one. I might support these, but it'd probably work because I put them near the edge. And these, or just don't tighten them too tight. That'd be kind of interesting to see what would work there. And I haven't built one, so I'd be interested if someone does. So here's some sketches. The CAD program I use is Autodesk Fusion 360. It's free for a hobbyist or a student or a company that doesn't make more than $100,000 a year. They let you use this for free. And it doesn't have the great drawing capability. Nowadays, most engineers just work inside a CAD system and they don't have to produce drawings. So it doesn't do a very good job of producing drawings. But this is the basic of my aluminum cart that I just designed but haven't built. It's got 70 millimeter wheels and it's like 52 millimeter roller skate wheels for the side wheels and up stops. And here's some more details. You could stop this and look at it if you're really interested in doing this. It's not that great of a drawing, but basically, I would give you this model in a STE. There's a couple of different model file formats that I can send this to, and you get it and read it in and just work from the model. Don't work from the drawings. That's how modern people do it. So now we're on to track. And I think I'll stop there and do track as a separate lesson. So, see you next time.